You know that feeling when you're staring at a completely blank white screen and that little loading spinner is just going round and round and round? Yeah, we've all been there. Welcome to this explainer. Today, we are diving straight into a full-on forensic investigation of a severely sluggish web app. We're going to figure out exactly how to hunt down those hidden performance bottlenecks and squash them for good.
So let's set the scene with a real-world ticket from a highly frustrated user. It reads, "The dashboard takes 8 seconds to load, and I have no idea where to start." Yikes. I mean, an 8-second load time? On today's web, that is literally an eternity. We know users will bounce after just 2 or 3 seconds of delay. But hey, when you're the dev staring down this bug report, looking at mountains of code, third-party libraries, and endless network requests, it is super overwhelming. But don't sweat it, we're going to apply a systematic approach to crack this case. Here is our case file index for today. 1. The app is slow mystery. 2. Profiling the crime scene. 3. Reading the flame chart. 4. Finding the heaviest operations. And 5. Catching render blocking scripts. Section 1. The app is slow mystery. Okay, when a user says the app takes 8 seconds to load, you really can't just guess what's broken. You need cold, hard evidence. That means securing our crime scene to get a clean diagnostic environment. Step 1. Always pop open an incognito window. Why? Because you absolutely do not want to spend 3 hours debugging a weird performance spike that turns out to be your ad blocker. Incognito strips away all that extension noise. Step 2. Open Chrome DevTools. Step 3, and honestly, this one is absolutely crucial. Enable CPU and network throttling. Look, your beast of a developer machine on fiber optic internet, that is not how your user is experiencing the app. Throttling lets you simulate the victim's actual device, like a mid-range phone on a spotty 4G connection. And finally, step 4, hit that record and reload button in the Performance tab to capture the whole loading sequence from scratch. Moving on to Section 2, profiling the crime scene. So your recording finishes and DevTools just throws this massive, intimidating wall of data at you. Take a breath. Let's break it down, starting right at the top in the summary timeline. DevTools relies on a very specific color coding system to tell the story. Think of it as your visual legend. Yellow, that means scripting, basically JavaScript parsing and execution. Green is rendering, which is the browser calculating layout and geometry. And purple is painting, where the browser is actually pushing pixels to the screen. If you're looking at that CPU chart up top and you see just a solid, saturated wall of yellow, well, you instantly know you've got a severe JavaScript bottleneck on your hands. The browser is completely maxed out just trying to think, which means it can't draw a single thing for the user. All right, Section 3, reading the flame chart. Now we're diving into the main thread flame chart, which is basically the central piece of evidence in this whole investigation. I want you to look at this chart kind of like a topographical map or a landscape. The x-axis going across represents time. So naturally, the wider a block is horizontally, the longer that specific function took to run. Wide blocks equal massive performance stress. Now, the y-axis going down vertically represents the call stack. It just tells you what called what. A function on top called the one right below it. And, a really deep stack isn't inherently a bad thing. It mostly just means your code is heavily nested, which is super standard if you're using React or Angular. Your eyes really need to be scanning horizontally, hunting for those massive, super wide blocks. Which brings us to defining public enemy number 1 in this landscape, the long task. A long task is any chunk of work on the main thread that takes longer than 50 milliseconds. But wait, why 50? Well, to keep your app running at a silky smooth 60 frames per second, the browser really only has about 16 milliseconds per frame to do its job. So if a script hogs the main thread for over 50 milliseconds, the browser is totally paralyzed. It can't update the UI, it can't respond to a user's click, it's frozen. And the best part? DevTools actually flags these for you. It slaps a little red triangle in the upper right corner of the block and fills it with red diagonal stripes. When you see those red triangles, bingo. You found the exact culprits causing all that layout jank and input delay. Let's jump to Section 4, finding the heaviest operations. Seeing those wide blocks visually is awesome, but to actually go in and fix the code, we need to transition from that visual map down to the raw data panels at the bottom. Before we look at the numbers, we have to make a super clear distinction between two metrics, total time and self-time. Total time is the full duration from the exact moment a function started until it completely finished, including all the time it spent waiting for its child functions to run. Self-time, on the other hand, is only the time spent executing code directly inside that specific function alone, completely ignoring its children. Think of it like a manager. A manager function might have a huge total time because they delegated a massive amount of work to their team. But their self-time is actually tiny because, well, they didn't do the heavy lifting themselves. We are hunting for the workers actually doing the grinding. We want to find the functions with incredibly high self-time. Down in that details pane, you've got 3 main tabs to help you out. The Summary tab gives you a quick, high-level breakdown of where the CPU spent its time, scripting, rendering, or painting. But honestly, the real magic happens over in the Bottom-Up tab. This tab takes all the activities and flattens them into a list. Here is the pro move. If you click that self-time column to sort it from highest to lowest, the exact piece of code causing your massive spike will literally float right to the top. It strips away all those managers and shows you exactly who is hogging the CPU. And finally, you have the Call Tree tab. This gives you a top-down view, which is absolutely brilliant for root cause analysis, like pinpointing exactly which innocent-looking click event kicked off that horrible chain reaction in the first place. And finally, Section 5, Catching Render Blocking Scripts. Okay, let's bring it all together and apply this exact workflow to the suspect holding our 8-second dashboard hostage. We load up the trace, and here's the story the data reveals. At 0 milliseconds, the network request kicks off. Cool. At 300 milliseconds, the browser starts parsing the HTML, but then, boom, it suddenly hits a script tag right in the head of the document. The browser is forced to drop everything. It has to download, parse, and execute this massive, heavy third-party analytics script. For over 7 solid seconds, the main thread is completely blocked. It finally finishes at the 7,500 millisecond mark. Only then does the browser get to calculate the layout, giving us our first contentful paint at exactly 8,000 milliseconds. The data perfectly illustrates how a single heavy third-party script can totally hijack your rendering path. The user stared at a blank screen for 8 full seconds, all because of one single line of HTML. Crazy, right?
So how do we actually clear this critical rendering path and neutralize the threat? Here's your remediation playbook. First up, slap some defer or async attributes on those non-critical script tags. That basically tells the browser, hey, go ahead and download this in the background, but whatever you do, do not stop building the page. Next, inline your critical CSS. Just move the styles needed for that above-the-fold content straight into the HTML head so the browser doesn't have to wait on an extra network trip before it can paint the screen. And third, use facades. If you've got a heavy chat widget or an interactive map, please don't load all that JavaScript up front. Show a lightweight static image or a fake button instead and only load the heavy stuff when the user actually clicks on it. It's a total game changer. As you go back to your code and start optimizing, there is one number I want burned into your brain: 50. 50. The ultimate goal of hunting down those red triangles, breaking up those long tasks, and deferring heavy scripts is to keep your main thread execution times strictly under 50 milliseconds. If you can respect that 50 millisecond budget, I promise you, your application is going to feel incredibly fast, responsive, and buttery smooth. So by simply using an incognito window with throttling, learning how to read the flame chart for long tasks, and sorting that bottom-up tab by self-time, you've effectively leveled up. You've gone from a frustrated dev guessing at problems to a precise forensic performance investigator. I want to leave you with this thought. When you open the DevTools performance panel on your own code base tomorrow, what hidden bottlenecks is your investigation going to uncover? Thank you so much for joining me for this explainer, and hey, happy debugging out there.